It is I, Caesar the Circulate, talking to you about arcs and chords. Now, excuse me, I need to go destroy the Statue of Liberty.
First thing we're talking about is a chord. Remember, a chord is a segment whose endpoints are on the circle. So here we have segment BF, and segment BF is a chord because both endpoints, point B and point F, lie on circle G. Same thing with segment DE down here. Segment DE would be considered a chord because both endpoints, point D and point E, lie on circle G. It's also important to note that the diameter of a circle would also be considered a chord. So if I were to draw a line segment connecting points B and D that passes through the center of the circle, point G, that segment would be considered both a chord and a diameter of circle G. Now, there are several different circle theorems we're going to talk about today. The first one says within a circle or incongruent circles, congruent central angles have congruent chords. So if we look at our example down here, what this is saying is that if you have congruent central angles, like angle PGN right here and angle LGM right here, we know that they are congruent, they're both x degrees. Because of that, the chords that connect the endpoints of those angles right here, so segment LM and segment PN, those would have to be congruent to one another. The second part says congruent chords have congruent arcs. So if I know that these two chords right here are congruent, segment PN is congruent to segment LM, then their arcs, arc PN and arc LM, must also be congruent to one another. And lastly, this says congruent arcs have congruent central angles. So to bring it all back together, arc PN down here, since that is congruent with arc LM down here, the central angles associated with those arcs, angle PGN and angle LGM, must also be congruent to one another.
After we take over New York, I'm going to call it the Big Apple. Example time.
Now example 1 says find the value of x. So x right here would be the measure of segment BD. That would be this chord right here. So we need to use what we just talked about in order to find the measure of segment BD, or x. Well, what are we given in this figure? We're given that the measures of these two central angles right here, angle BCD and angle ACE, are equal to one another, meaning that these two central angles then would be congruent to each other. And since we know that these two central angles are congruent, we just said that congruent central angles have congruent chords, meaning that this chord over here, segment BD, must be congruent to this chord over here, segment AE. Now, since you know that those chords are congruent to each other, you know that their measures must be equal. So, if the measure of segment AE is 20.3 inches, that means the measure of segment BD must also equal 20.3 inches. So that would be our value of x. Part B, we again want to find the value of x, and x in this case would be the measure of angle HKI. Well, we are given the measure of segment GJ right here, this chord, is equal to the measure of segment HI, this chord over here. Because these measures are equal to each other, that means these chords are congruent to one another. And what do we know about congruent chords? We know congruent chords have congruent arcs. So arc GJ over here would have to be congruent to arc HI over here, meaning that if the measure of arc GJ over here is 84 degrees, the measure of arc HI over here must also be 84 degrees. Now again, we are trying to find this angle in here, angle HKI, that's where our x is. So how do we do that? Well, what do we know about congruent arcs? Congruent arcs have congruent central angles, meaning that this angle in here, angle HKI, must be congruent to angle GKJ. But the issue is we don't have either of those measures. Well, we do know over here that the measure of a central angle is equal to the measure of its intercepted arc. So in this example, angle GKJ intercepts this arc right here, which is 84 degrees, meaning that the measure of this central angle is 84 degrees also. You could have done the same thing over here because we know that angle HKI intercepts this arc, whose measure is 84 degrees. We know that x must also be 84 degrees. So that is your answer here.
What kind of key opens a banana? A monkey. Oh, you tried.
Okay, part A, doing the same thing. We want to find the value of x, and x in this case would be the measure of arc LJ over here. So how do we find the measure of this arc? What are we given? We're given that the measure of angle GKJ in here is 141 degrees. We're given that the measure of segment GJ is 12 feet, and we're given that segment GJ is congruent to segment LJ. Now, since both of these segments are chords of circle K, we know that we have congruent chords here. And what do you know about congruent chords? Well, we just said congruent chords must have congruent arcs. meaning that this arc over here, arc LJ, must be congruent to this arc over here, arc GJ. So all we have to do is find the measure of this arc over here, and we'll figure out x. So how do we find the measure of arc GJ over here? Well, the measure of arc GJ, we just said the measure of a central angle is equal to the measure of its intercepted arc. So if the measure of this central angle is 141 degrees, the measure of the intercepted arc, the measure of arc GJ, must also be 141 degrees. And since these two chords are congruent, that means these two arcs must also be congruent. So their measures must be equal. Therefore, x has to equal 141 degrees. Part B, doing the same thing. We're again given a circle, we're given a couple chord measures, and we're given an arc measure, and we're trying to find the measure of this arc right here. So what do we know? We know that the measures of each of these chords are equal, meaning that these two chords are congruent to one another. And what do we know about congruent chords? We know that congruent chords must have congruent arcs, meaning that arc BE would be congruent to arc EA over here, meaning that their measures would be equal to each other. So if the measure of arc BE is x degrees, that means the measure of arc EA would also be x degrees. Well, how does that help us? Well, if you notice, these three arcs here, arc BE, arc EA, and arc AB, form a full circle, meaning that their measures should add up to 360 degrees. So now I can just plug in what I know. I know the measure of arc AB is 150 degrees. That goes in here. Measure of arc BE is x. That goes in here. The measure of arc EA down here is x. That goes in here. Then we just solve for x. X plus x is 2x. Subtract both sides by 150. Divide both sides by 2. I get x has to equal 105 degrees. That's the measure of each of these arcs. Now let's talk about a couple new circle theorems. So the first one says, within a circle or congruent circles, chords equidistant from the center are congruent. So in this figure down here, you see we have two chords, segment PN and segment LM. They are the same distance from the center point, point G. We know that because segment GR and segment GT are congruent to each other. Because these two chords are equidistant from the center of the circle, these two chords then must be congruent to each other. The second part of this now says congruent chords are equidistant from the center. So let's say I didn't know that these two chords were the same distance from the center of the circle, but instead I was given that these two chords are congruent to each other. Then I know just because these two chords are congruent to each other, they must be the same distance from the center of the circle. Example 2 says find the value of x. So we're again given a circle and we're given a few measurements in here. And we want to find x, which would be the measure of segment PN, one of our chords. Well, what do we know about these two chords? Well, we see that they are actually equidistant from the center of the circle. The measure of segment GS is equal to the measure of segment GR. They're both 6 centimeters. Because these two chords are equidistant from the center of the circle, we know that these two chords then must be congruent to each other, meaning that their measures must be equal. So to find the measure of segment PN, or x, all I have to do is figure out what the measure of segment LM is. Well, how do I find the measure of segment LM? I only have half of it, the measure of segment LR. Well, these two tick marks tell us that this segment right here would be congruent to this segment right here, meaning their measures must be equal to each other. So I know that the measure of segment LM, this chord right here, would be 14 centimeters. And since these two chords are equidistant from the center of the circle, they must be congruent, meaning their measures must be equal to each other. So the measure of segment PN has to be 14 centimeters, meaning x has to be 14 centimeters. Part B, I now have a circle where I'm given the measure of a couple of the chords, but I'm not given the distance that they are from the center of the circle. Well, I can see that the measures of these two chords would both be 11 inches, meaning that these two chords then would be congruent to each other. And what do we know about congruent chords? We know that congruent chords must be equidistant from the center of the circle, meaning that this segment right here, segment PR, has to be congruent to segment PU, meaning their measures must be equal. So if the measure of segment PU is 3.7 inches, that means our x here, the measure of segment PR, would also be 3.7 inches.
Why don't monkeys play cards in the jungle? There's too many cheetahs! You try! Ho!
Okay, again, we want to find the value of x, and x in this case is part of the measure of segment GR here. So how do we do this? Well, we see from this figure that we have segment PN and segment LM that are both chords of circle G. And it looks like those two chords would be congruent to each other. So what do we know about congruent chords? We know that congruent chords must be equidistant from the center of the circle, meaning that segment GR in here must be congruent to segment GT over here, meaning that their measures must be equal to each other. So I can then plug in x squared minus 4 for the measure of segment GR, plug in 5 feet for the measure of segment GT. Now all we have to do is solve for x. So how do I solve this for x? Well, to get x by itself, I would add 4 to both sides. I would then square root both sides of the equation. And remember, when you square root a variable that is squared, on the opposite side of the equation, you got to put plus or minus. So over here, the square root and the square cancel each other out. And on this side, we take the square root of 9, which is going to be plus or minus 3. And both of those would be your answers here. Now, normally, we only take the positive version, but here it can be both positive or negative 3, because if you were to plug either of those in for x up here, you would get a positive length for the measure of segment GR. That's why you take both positive and negative 3 as our answer. Part B, we again want to find x, and x is part of the measures of each of these chords. Well, what do we know about these chords? Well, we know that they are equidistant from the center of the circle because both of these are 6 centimeters. Because both of these chords are equidistant from the center of the circle, we have a theorem that tells us that they must be congruent to each other, meaning segment AB over here must be congruent to segment DC down here, meaning their measures must be equal. So I can now plug in what each of those measures are equal to, and I could solve for x. So how do I solve this for x? Well, I subtract x from both sides of the equation. I add 1 to both sides of the equation, divide both sides by 4, and I get x is equal to 3.25. Now, there's a couple more circle theorems we need to talk about. The first one says, in a circle, a diameter that is perpendicular to a chord bisects the chord and its arc. So down here, we have a diameter of circle G, segment PN, and we see that is perpendicular to this chord right here, segment LM. Because of that, this theorem says that the diameter will bisect the chord, meaning that it will cut it in half. So segment RM down here would be congruent to segment LR up here. Now, the theorem says the diameter not only bisects the chords, but it also bisects its arc. So this arc over here, arc LM, will be bisected. It will be cut in half, meaning arc LN would be congruent to arc NM over here. This arc over here, arc LPM, would be bisected. It would be cut in half, meaning arc LP or PL would be congruent to arc PM or MP over here. The next circle theorem we need to talk about says, in a circle, a diameter that bisects a chord that is not a diameter is perpendicular to the chord. So in this figure, we have segment PN as a diameter of circle G, and we know that it bisects segment LM right here, this chord. Because it bisects this chord, we know that it also must be perpendicular to that chord. Now notice it says a chord that is not a diameter, because if the chord were a diameter, it doesn't necessarily have to be perpendicular to the other diameter. The last circle theorem we're going to talk about says, in a circle, the perpendicular bisector of a chord contains the center of the circle. So in our figure, we again have segment LM as a chord of circle G. Now notice this segment right here, segment PN, not only bisects segment LM, this chord, but it's perpendicular to it. Because of that, we know that segment PN must contain the center of the circle. Now note that it doesn't say it must be a diameter, because technically this chord could be bisected and perpendicular to a radius as well, and it would still contain the center of the circle. Now example 3 says find the value of x, leave answer in simplest radical form. So we again are trying to find x, and x in this case would be the measure of this chord. Well, how will we go about solving this? Well, we know that since this chord right here is perpendicular to this segment, and this segment contains the center of the circle, that means it must bisect this chord over here. So these two segments then would be congruent to each other. Well, that still doesn't help us. Well, let's try to find half of this then, and we can just multiply that measure by 2, and that'll give us the measure of x, our chord. So how would we find half of this? Well, let's just call this segment right here what we're going to try to find b. How would I find b? Well, I have created this little right triangle here. And in this little right triangle here, we are given 2 side lengths. So how do we find the missing side length of a right triangle? We use the Pythagorean theorem. A squared plus b squared is equal to c squared. And remember, the only one that matters where you plug in is your hypotenuse. Your hypotenuse, the side opposite your 90-degree angle, has to be your c value. So I'm going to take 5, plug it in for c, and I can take 2, plug it in for a or b, take b, plug it in for a or b. But since it's already b, might as well plug in b for b and 2 for a. Now I can simplify. 2 squared is going to give me 4, 5 squared is going to give me 25. I then subtract 4 on both sides. I get b squared is equal to 21. Now all I have to do to get b by itself is take the square root of both sides. Remember, when you square root a variable squared, on the other side you need to put plus or minus. Now over here, the square root and the square cancel each other out. On this side, there's no perfect square that goes into 21, so we're just going to leave it rad 21. And since we're dealing with measurements in a circle, we're just going to keep the principal root, the positive version, and say that b is equal to positive rad 21. 21 inches. We can't have a negative measurement in our circle. Now that is the length of half of this chord. I need to find the length of the entire chord. So what I do is take what I found for B, multiply it by 2, and I get that x has to equal 2 rad 21 inches. Part B, I am again finding x, and x this time is just this little tiny segment right here. So how would I solve this? Well, notice that this diameter and this chord are perpendicular to each other. We also know that we're given the radius of this circle. So the way you're going to solve a problem like this is you're going to take this radius, 8 meters, and you're going to swing it down here and connect it with this endpoint of our chord. The reason I do that is because I now have created this right triangle here, and I'm given two sides of the right triangle, and I'm trying to find the third, meaning I can use the Pythagorean theorem in order to solve for x. Remember, it only matters what value you plug in for c. It has to be your hypotenuse, the side opposite the 90-degree angle. So I'm going to plug in 8 for c, and then I can plug in x and 4 for either a or b. Now all I have to do is solve for x. So I square each of these. I then solve for x by subtracting 16 from both sides, square rooting both sides, and remember, when you square root a variable squared, you have to put plus or minus on the other side. Now we can simplify. Over here, the square root and the square cancel each other out. On this side, I can actually simplify rad 48 a little bit further. Are there two radicals that multiply together to make rad 48, one of which is a perfect square? Yeah, that would be rad 16 times rad 3. I do that because 16 is a perfect square and the square root of 16 is 4. So this becomes 4 rad 3. Now instead of writing plus or minus, I'm just going to use the principal root, the positive version. The reason is because I'm dealing with measurements in a circle and I can't have a negative measurement in my circle.
What did the monkey bring to the party? Chips and dip! Oh, you try!
Okay, we again want to find the value of x. So where's x here? X would be this segment right here. Well, in this figure, we have a diameter that bisects a chord. And we just learned from one of our theorems that when a diameter bisects a chord, they are perpendicular to one another. So how does that help us? Well, it doesn't help us right now. Let's see if something else can help us. Well, we know the radius of this circle is 3 centimeters. And we know that the measure of this segment right here is 1.8 centimeters. So 3 centimeters minus 1.8 centimeters would give you the measure of this segment right here, which is 1.2 centimeters. Okay, still not sure how that helps us, but we need to find x. Well, can we do something with the Pythagorean theorem like we were doing? Yeah, here we have a radius equal to 3 centimeters. So what we can do is we can swing that radius down here and connect it to the endpoint of this chord. Now we have created this right triangle where we're given 2 of the side lengths and we need to find the third, meaning we can use the Pythagorean theorem in order to solve for x. Now, it only matters which value here you plug in for c. C has to be the hypotenuse, the side opposite your 90-degree angle. So 3 is going to go in for c, and then I'm going to plug in 1.2 for my a, x for my b. You could have switched those, you would get the same answer. So now we just need to solve for x. So 1.2 squared is going to give you 1.44, 3 squared is going to give you 9. Solving for x, we subtract 1.44 on both sides, then we square root both sides to get rid of this square. When we square root a variable squared, on the other side we need to put a plus or minus. On this side, the square root and the square cancel each other out. On this side, because it says round to the nearest tenth, you can just put this in your calculator. And remember, we're only taking the principal root, the positive version, because we're dealing with measurements in a circle. So we get that x is approximately equal to 2.7 centimeters when we round to the nearest tenth. Part B, doing the same thing, except this time we're trying to find the measure of this segment right here, which is our x. So how are we going to do this? Well, we are again given a radius measure. In this case, it's 15 inches. What we can do is again swing our radius up and connect it to the endpoint of this chord, creating another small right triangle here. But wait, that doesn't help us find x here. Well, yeah, it does. If I can find the measure of this little segment right here and subtract it from 15 inches, that will give us the measure of x here. Okay, so I need to find the measure of this little segment here. We'll call it a. So again, I have a right triangle. I'm given 2 side lengths of that right triangle. I just need to find the third. So I use the Pythagorean theorem to find our a. Again, it only matters which value here we plug in for our c. That's going to be the hypotenuse, the side opposite the 90-degree angle. So that would be this 15 inches. So I'm going to take 15 inches, plug it in for c. A and 11 inches, I can plug in for a or b. Well, since a is already a, I'm going to plug that in for a, take 11 inches, plug it in for b. I can then solve for a by squaring each of these these, subtracting 121 on both sides, square rooting both sides. And remember, when you square root a variable squared, on the other side you need to put plus or minus. Here, the square root and the square cancel each other out. On this side, we're just going to take the principal root, the positive version, because we're dealing with measures within a circle, and we can't have negative inches. Now, we don't want to just plug this in our calculator yet and round, because this is not what we're trying to find. We're trying to find x, not a. So we want to leave this as exact as possible. So we're going to simplify this by breaking it up into two radicals that multiply together to make rad 104, one of which has to be a perfect square. Well, that would be rad 4 times rad 26. So we end up getting positive 2 rad 26 inches as our measurement for a. But again, that's not what we're trying to find. We're trying to find x. So what do we know about x? We know that a plus x has to equal this 15 inches, the full radius. And we know that a is equal to 2 rad 26. 15 inches is our radius. So now all we have to do to solve for x is just subtract 2 rad 26 from both sides. Plug that in our calculator. We get that x is approximately equal to 4.8 inches. Now, a word problem says the snowboarding rail shown is an arc of a circle in which segment BD is part of the diameter. If arc ABC is about 28% of a complete circle, what is the measure of arc AB? So let's first take a look at what this looks like. We have this arc right here, arc ABC, that is 28% of a complete circle, where segment BD is part of the diameter. So let's draw our full circle where segment BD is part of our diameter. So it's going to look something like this. Now, this question wants us to find the measure of arc AB right here. Well, in this question, we're not given any information about the measure of arc AB. The only information we're given is that arc ABC is 28% of a complete circle. Well, if we know arc ABC is 28% of a complete circle, can we figure out the measure of arc ABC? Yeah, and then that will probably help us figure out what the measure of arc AB is. So let's find the measure of arc ABC. Since we know that arc ABC is 28% of a complete circle, what we can do is we can take 360 degrees and just find 28% of that. That'll give us the measure of arc ABC. So how do I find 28% of 360 degrees? I take 28% as a decimal, 0.28, multiply it by 360, and it gives me the measure of arc ABC, which is 100.8 degrees. So now, how is that going to help us find the measure of arc AB right here? Well, since we know that segment BD is part of the diameter here, and it's perpendicular to what we now see is a chord, segment AC, then we know that this segment right here must bisect the chord and its arcs, meaning that these two arcs right here, arc BC and arc AB, must be congruent to each other. And if they're congruent, that means their measures are equal. And if we know the measure of the whole arc, we can just figure out the measure of half of the arc, the measure of arc AB, by taking what the measure of the whole arc is equal to and dividing it by 2, or multiplying it by half. And we end up getting that the measure of arc AB is 50.4 degrees. Woo!